Good morning. Here we are going to study the last two colligative properties of this unit: depression in freezing point and osmotic pressure. Now, first, depression in freezing point. Solution freeze at lower temperature than pure liquid. This we can see in de-icing scheme that use salt, calcium chloride or urea to melt the ice on the road. You must be knowing that. And in the use of ethylene glycol as an antifreeze in automobile radiator. So the lowering of vapor pressure of a solution causes lowering of a freezing point compared to that of a pure solvent. We know that freezing point of a substance. The solid phase is in dynamic equilibrium with the liquid phase. Thus, freezing point of a substance may be defined as the temperature at which vapor pressure of the substance in its liquid phase is equal to vapor pressure in the solid phase. A solution will freeze when its vapor pressure equals the vapor pressure of pure solid solvent, and is clear from the diagram. Now, according to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases. Now it would become equal to that of the solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. Suppose TF0, freezing point of pure solvent. TF, its freezing point when non-volatile solute is added to it. So decrease in the freezing point will be this one. Now, in general, we know that the liquid will freeze when the chemical potential of solid is this. As the freezing point of the solvent in a solution will be affected by anything that changes the chemical potential of the solvent, it turns out the chemical potential reduced by the presence of the solute. So, in a mixture, the chemical potential of component A can be calculated as mu A is equal to this one. And because Xa, it is always less than or equal to 1. So chemical potential is always reduced by the addition of another component. So simple. The condition when it freezes is this one. Both the mu A, solid and liquid, should be equal. So the equation will rearrange to mu minus mu 0A upon RT will be equal to ln of Xa. Now, to evaluate the temperature dependence of the chemical potential, it is useful to consider the temperature derivative at constant pressure. We will see its derivative at constant pressure. So we will get these terms when we differentiate it with respect to T at constant P. Now we also know that mu is equal to H minus Ts. Mu is G, no? So del mu by del T, it is minus delta S. So this equation, we will keep the values as HA minus TSA, H0A minus TS0A, like this. So replacing the terms, we get this one. Actually, this H, difference between this H is delta H of fusion. So the equation becomes like this. These two term will be cancelled and the equation reduces to this one. So we will get the value of ln Xa as this. Now again it follows that 1 by t minus 1 by t0 we can write down like this. So putting the values, we are here. Now as the amount of solute present is very small, so xb very less than 1, we can write down this one. So delta T will be this one and we reach to this conclusion. What is this Kf? Kf is nothing but this factor. Freezing point depression constant. Freezing point depression constant. Or it is known as molar cryoscopic constant, Kf. It has the unit of this. Now this delta T, it gives the magnitude of reduction of freezing point for the solution. Now delta heat of fusion, T0, these are the properties of the solvent. So freezing point depression property is independent on the solute. And it is a property based solely on the nature of the solvent only. Now since mole fraction of XB, this was introduced as 1 minus XA, so it is important to keep in the mind that for a real solution, freezing point of the solvent changes the composition by decreasing the mole fraction of the solvent and increasing the mole fraction of the solute. Magnitude of delta T will change as the freezing process continuously removes the solvent from solid phase. Now again we can keep that mole fraction, we can replace it by the terms of m is equal to W2 upon M2 upon W1 upon 1000. We can keep the values and we can find out the expression for Kb. In this Kb expression, the molar mass can be determined. So the values of Kf, Kb, all these values, they depend on the nature of the solvent and not on the solute. This delta H, fusion or vaporization, they represent the enthalpies for vaporization as well as the fusion. So this is all about the Kb. Molar freezing point depression constant. Again, the numerical can be asked on this. You can be asked to derive the expression and then the numerical you have to solve by putting the values. So you should be habitual of deriving all the colligative properties. It's expression for calculating the molar masses. Now next and the last important property is the osmotic pressure. A number of natural material exhibit selective permeation, meaning that the only molecules of a certain size, shape, polarity, charge selectively, they are capable of passing through the membrane. Biological tissues, cells, we know that. So these materials are referred as a semi-permeable membrane. Now consider the apparatus which is shown here, in which sample of pure solvent and a solution, they are separated by a membrane known as semi-permeable membrane, in which only solvent molecule may penetrate. Solvent molecule will diffuse across the membrane. See, this is solvent, this is solution. Solvent is penetrating here. Level is increased till an equilibrium is reached. And when the equilibrium is reached, the difference in the level, the pressure generated due to this is known as osmotic pressure. It results in a net transfer of solvent molecule from pure solvent to the solution section. This diffusion driven transfer of solvent molecule, it is known as osmosis. This process is known as osmosis. The volume of a solution increases as it becomes diluted by the coming solvent. So level rises. So it increases the hydrostatic pressure, that is due to the weight of the column of the solution. See, its height is less, its height is more. So whatever may be due to the height, weight of the column, the pressure, it rises. And it results in a faster transfer of solvent molecules back to the pure solvent side. Means this pressure pushes the solvent molecules back. When the pressure reaches to the value that is a reverse solvent transfer, the rate is equal to osmosis rate and the equilibrium is attained. That time, whatever may be the pressure, that is osmotic pressure. The nature of the osmosis and the magnitude, it can be understood by examining the chemical potential again for pure solvent and that of solution. Now we know that for pure solvent it is written as this, as Xa always less than 1. Again, chemical potential of the solvent in solution is always lower than that of solvent. So to prevent osmosis, the rate of chemical potential of the solvent in the solution, specifically the process of osmosis will stop when the chemical potential of the solvent increase to the point of which is being equal to that of pure solvent. Means chemical potential mu 0 A will be equal to xb plus some pressure pi. Now, to solve the problem, to determine the magnitude of this pressure, the pressure dependence of the chemical potential is needed in addition to the understanding the effect of the solute, which has on lowering the chemical potential. The magnitude therefore increase in chemical potential due to application of excess pressure. Now we know this expression. The increase in chemical potential due to application of excess pressure is given by this one. On integrating, we reach to here, and following some mathematical steps, we come to find out the pi osmotic pressure. Vm is the molar volume. So xb upon Vm, the concentration of the solute B. When the pressure exceeding the osmotic pressure pi, it is applied to the solution, the chemical potential of the solvent can be made to exceed the pure solvent on the other side of the membrane, causing reverse osmosis. So this is very effective method for example in the recovering of pure water from the mixture of salt solution, this osmotic pressure. So this is a very good method used many places. It has many application also. Now the last part is the abnormal colligative properties and the Van 't Hoff factor. Since colligative properties depend on the number of particles of the solute, in some cases where the solute associate or dissociate, abnormal results are obtained. So Van 't Hoff factor. Van 't Hoff factor, in order to account for all abnormal cases, where I is the observed colligative property, actual and the theoretical. Means number of molecules actually present and the number of molecules expected. So this is the ratio, that is Van 't Hoff factor. Why association? We know that there are many organic solute which in non-aqueous solution undergoes association to form the bigger molecule. The number of effective molecule decreases, and so osmotic pressure, elevation, boiling point, depression, all the colligative property, it is less than that calculated on the single molecule, because colligative property depend on the number of molecules. But as the number of solute molecules are undergoing association, so number of solute molecule n, that number will decrease, and that will severely affect the colligative properties. For example, acetic acid in benzene or chloroacetic acid in naphthalene, association of acetic acid occurs through the hydrogen bonding. So association occurs, and the degree of association, that is the fraction of total number of molecule which associate to form bigger molecule. We can consider this equilibrium Na, solute particles, n number of solute particles associated to form A, n times. Suppose A is the degree of dissociation, then the number of undissociated molecule will be 1 by A, and the associated molecule will be A by N. Total moles will be this one. I can be calculated by this method. So we can use such type of expression or method for calculating the abnormal colligative properties. This is all about the colligative properties. Now you have to derive the expressions at your own. You have to practice it. You have to see the expressions for colligative properties which you have to use successfully in solving the molar mass problems.